All right, today we're going to dive into one of the most fundamental ideas in, well, all of mathematics, set theory. Now, I know it might sound a little complex, but at its heart, it's a really simple, powerful language for grouping and organizing pretty much anything. From your favorite songs to the planets in our solar system, set theory gives us the tools to see the hidden structures that are all around us.
So, let's just jump right in with a question. Think for a second about your favorite playlist. Got it? Okay, now think about the planets that orbit our sun. On the surface, those two things seem like they have absolutely nothing to do with each other. But believe it or not, mathematically, they share a really fundamental connection. What could it possibly be?
And the answer is, they're both sets. It's that simple. A playlist is just a collection or a set of songs, and the solar system is a collection of planets. Set theory is the formal language that lets us talk about these collections with real precision, whether we're discussing music, planets, or even complex data.
That keyword, set, is what this is all about. So what exactly is a set? To really get a handle on its power, we first need to learn the basic rules of the game. The guy who came up with this whole idea was a German mathematician named Georg Cantor. He gave us this simple, but honestly pretty profound definition. A set is a collection of definite and distinguishable objects. That little phrase is the bedrock for everything else we're going to talk about. So let's break that down just a little more formally. A set is a collection of distinct elements where the order doesn't matter. Those two rules, distinct elements and order doesn't matter, are absolutely crucial, and we're about to see exactly why.
Okay, this slide perfectly illustrates our two rules. First, the elements have to be distinct. I mean, you wouldn't list Earth twice in a set of planets, right? That wouldn't make sense. Second, the order is totally irrelevant. The set Earth, Mars, Jupiter is the exact same set as Mars, Jupiter, Earth. And hey, for any of you programmers watching, this should sound super familiar. It's kind of like a unique array or a hash set where duplicates get ignored and the order doesn't change the collection's identity one bit.
All right, so we've got the basic rules down. Now let's learn how to speak the language. Just like any field, set theory has its own special vocabulary, and getting a handle on it is the very next step. First up, the items inside a set aren't just things or objects. We have a specific name for them, elements. So in our planet set, Earth is an element. Mars is an element. See? Simple, right? Now, to say that something is an element of a set, we use this cool symbol here that looks kind of like a curvy E. So if we have a set A that's just 1, 2, 3, we'd write that 2 is an element of A. And to say something is not in the set, you guessed it, we just draw a line right through that symbol. So in this case, 5 is definitely not an element of A.
Okay, so we know what a set is and what to call its parts, but how do we actually, write one down, especially if it's a huge one? Well, it turns out there are two really powerful ways to do it. You can either list the elements out one by one, or you can describe them using a rule. These two methods have their own formal names: roster notation and set builder notation. You can think of roster notation like calling the roll in a classroom. You're just listing every single element by name. Set builder notation, on the other hand, is more like posting a job description. You state the requirements an element has to meet to get into the club. Let's look at roster notation first, because it's the most direct. For the set of vowels, you just list them: A, E, I, O, U. And you stick them inside some curly braces. Easy. For the odd numbers less than 10, same deal. You just list 1, 3, 5, 7, and 9. Super straightforward. But now, check out set builder notation. Instead of listing everything, we just define a property. For the vowels, we say the set contains any element x such that x is a vowel. For those odd numbers, we can say it's any x such that x is between 1 and 10, and x modulo 2 is not 0, which is just a fancy math way of saying it's not an even number. This method is incredibly powerful, especially when you're dealing with really big or even infinite sets.
The best way to get really comfortable with these is to just practice switching between them. So come on, let's try a couple together. All right, here's our first challenge. We've got set A written in roster form as 1, 2, 3, 4, 5. So what's a rule that describes all of these elements and only these elements? Just take a second and think about it. And there it is. We could say that A is the set of all elements X, such that X is a whole number, and X is greater than or equal to 1, and less than or equal to 5. That rule perfectly nails everything on our list.
Okay, let's flip it around and go the other way. Here's set C, described with a rule. X is a multiple of 3, and it has to be between 3 and 15, including both 3 and 15. So can you list out all the elements that actually fit that description?
And here we go. The multiples of 3 that fit our rule are 3, 6, 9, 12, and 15. See, the big takeaway here is that both notations are describing the exact same set. They're just doing it in different ways.
So, we know what a set is, how to speak its language, and 2 different ways to write it down. The next logical question seems pretty simple. How do we measure how big a set is?
Well, in set theory, the size of a set gets a special name, cardinality. Yeah, it's a bit of a fancy word, but all it means is the number of elements in the set. And we show it by putting these vertical bars around the set's name.
So, if we have the set 1, 4, 3, 5, we can just count the elements. 1, 2, 3, 4. There are 4 of them. So we say the cardinality of this set is 4. Yep, it's really that simple. But cardinality gets really powerful when we start using it to compare different sets. If 2 sets have the exact same cardinality, it means we can make a perfect one-to-one match between all of their elements. If one set's cardinality is smaller, we know for sure there are going to be elements left over in the bigger set after we try to pair them up. This seemingly simple idea actually has huge implications in higher-level math.
So as we start to wrap this up, I hope it's clear that sets are so much more than just simple lists. By giving us these precise ways to define, write, and count collections, they really become the fundamental alphabet for huge fields like logic, database theory, and computer science. They are the basic building blocks for how we structure information in our modern digital world.
Learning this language of sets gives you a brand new, powerful tool for seeing the hidden structure in the world all around you. So now that you've got this alphabet of logic in your back pocket, the only question left is, what are you going to build with it? Thanks for tuning in to This Explainer.